In Lesson 4, we're working with finding equations of tangent lines as well as applying the mean value theorem. So recall that from middle school or from Algebra 1, we know that an equation written y equals mx, that's the equation of a line that passes through 0, 0 with a slope of m. And so if we think about transformations, as we often do in Algebra 2, we know that if we were to think of this as y equals m times x minus h plus k, I could think of that as the original line, mx, that has been translated horizontally to the right h units, vertically up k units. In other words, I could think of that as being the equation of a line that passes through the point, the ordered pair hk, with the slope of m. And so we know y equals mx plus b is what we call slope-intercept form of a line. This is called point-slope form of a line. So we might think of point-slope form of a line. I could subtract my constant over, and I might think of that as what is written in this box. Y minus k equals m times x minus h, and in that case, h comma k is our point on the line, and m is our slope. Now, more commonly, if you were to open up a textbook or just even do a Google search for point-slope form of a line, you might more commonly see y minus y sub 1 equals m times x minus x sub 1, where x sub 1 comma y sub 1 is the point on the line. That's the ordered pair. This works either way. It's just different notation. The reason that I kind of like writing it the second way with the x sub 1 and the y sub 1 is that if you ever forget the equation, if you ever forget how to write point and slope, think about how we find slope. We find the slope of a line by subtracting two ordered pairs. So subtracting, finding our difference in y values, so y2 minus y1, over our change or difference in x values, x2 minus x1. And if I wanted to make the slope a function of any x and y, I could just delete those 2's and think of that as y minus y1 over x minus x1, where x and y are variables. So now, if I wanted to take my slope formula and turn it into this point and slope equation, I could do so by multiplying both sides of my slope formula with my denominator x minus x sub 1. And when we do that, that kind of cancels out on the side. And so using the reflexive property, I'm going to put my y's on the left. Y minus y1 is just my slope times x minus x sub 1. So I don't care what notation you use because we're about to actually get a third one. All right, so we said to find the equation of a tangent line, we need to know a point on the tangent line and the slope of this tangent line. And so it is a good thing for us that that point does not specifically have to be the y-intercept. It would be much harder if we always had to know our y-intercept. So let's assume that our point on the line is going to happen right here at A, so where x is equal to A. And we call this ordered pair here, so this ordered pair would be A comma f of A. We call this the point of tangency. Point of tangency. So the point of tangency is the point at which our tangent line locally intersects our curve in just one place. Well, one place locally. So if we are trying to write our equation of the line, I'm still going to use x and y. I know that I might start with my point and slope form. So I might start with my y minus k or y1, however you want to write that, times my slope times x minus h or x sub 1. And now if I think about it, my ordered pair is a comma f of a. So instead of y sub 1, that's going to be my f of a. Instead of x sub 1, that's going to be my a value. And then the other thing we want to remember is the thing that gives us the slope of the tangent line is our derivative. So in point and slope form, what is our m, the slope of a line, that's going to be our slope of our tangent line and evaluated at that particular value of a. So this becomes f prime of a here. All right, so when we look at how to write the equation of a tangent line, again, this is in point slope form. where a comma f of a is our point, and f prime of a, our derivative at that particular value, is our slope. So let's look at this first example. We're asked to find the equation of the line tangent to f at x equals 3, and then we're going to use that to approximate f of 3.1. So if I think about the things that I need for my equation of a tangent line, I need my point of tangency, which is like a comma f of a, and I'm already given that a is 3. So what that means is I need f of 3. I also need my derivative evaluated at 3. So again, f prime of 3, that's going to give me my slope. So sometimes I like to just jot down for myself what I'm going to need to find in order to accomplish this equation. All right, so it does not matter in which order we find these things. I like to find f of 3 first. That seems like the easier thing to do. So f of 3 is 3 squared plus the square root of 3 plus 1. So that is what, 9 plus 2? Oh no, wait, sorry, not plus, times. Wow, it would really help if I read. Sorry, 3 squared times the square root of 3 plus 1, which is 9 times 2. So 18. So again, when our input is 3, our output's 18. So 3 comma 18 is our point of tangency. So if you see me write POT, that's just standing for point of tangency. All right, the next thing that we need to find is f prime of 3. And in order to find f prime of 3, we need to find f prime of x. So we need our derivative as a function of x first. So in order to do that, I'm going to rewrite f, and I'm going to think of that as x squared times x plus 1 in parentheses to the 1/2 power. Oh, so it looks like I'm going to have to use both the product rule and the chain rule to find my derivative. So I notice that f is a product of x squared and another factor, x plus 1 to the 1/2 power. And that second factor, x plus 1 to the 1/2 power, is a composition. So when I'm using the product rule, I'm going to do my derivative of the first thing. So my derivative of x squared times my second factor, x plus 1 to the 1/2 power, plus the derivative of my second factor. This is where we have to use the chain rule, but the good news is that when we're thinking about the chain rule, the derivative of x plus 1 is just 1. So I don't actually, I can show that I'm multiplying by 1. That doesn't change anything. And then I need to multiply by my first factor, so x squared. So we don't have to clean this up all the way, but we want to clean this up so that it's easier for us to work with. So again, if I try to clean up this derivative, I might think of this as like 2x times the square root of x plus 1, plus I definitely want to personally get rid of that negative exponent for my own wellness. So plus I have 1x squared on top over 2 times the square root of x plus 1. Now, if you wish, you could go on to get common denominators there, but again, our end goal is to get an equation of a tangent line. And since we're trying to find f prime of 3, I think we could just manipulate f prime of x until it's something we're comfortable working with, and then plug in a 3. So I'm feeling pretty good about how we have f prime of x written. So I'm going to plug in my 3 now. So 2 times 3 times the square root of 3 plus 1 plus 3 squared over 2 times the square root of 3 plus 1. So we end up getting like 6 times 2, the square root of 3 plus 1 is 2, plus 9 over 2 times 2, so 9/4. So we have 12 plus 9/4, which is like, what, 48/4 plus 9/4, which is 57/4. So f prime of 3 is equal to 57/4. All right, so now we are ready to write our equation of our tangent line because we have everything we need. We have a point and we have our slope. So y minus 18, so again, that's our output from our point of tangency, is equal to our slope, so 57/4. times x minus 3. Again, that 3 was from our point of tangency. All right, so that is the equation of our tangent line. And you can absolutely leave it like that. It would also be just fine to add the 18 to both sides. So if you wanted to write it as 57/4 times x minus 3 plus 18, that's fine. I think that's going to help us for the next thing we do. But I would strongly encourage you, do not distribute that 57/4. Just leave it. Because if you distribute that, you try to combine like terms, you're just inviting possible mistakes. And if you had the correct equation, but you make a mistake when you distribute, you're going to lose your correct answer. So you're going to lose your answer point. We don't want to do that. All right, the last task, we do this a lot with tangent lines. We are asked to use this line to approximate f at f of 3.1. So if I'm finding f of 3.1, well, I would need to know, I'd need to know my function f, which we're given. But if I plug in 3.1 to this function, and I'm not using a calculator, I have to square 3.1. I have to think about the square root of 3.1 plus 1. That gets really gnarly. That gets really gross really fast. So oftentimes, we will use a tangent line to do what is called a linear or a local linear approximation, meaning that if I have my tangent line, I'm going to go up to this picture for just a second. If my tangent line is, if I drew in my tangent line at the point where x is equal to a, I might use that to approximate a value on my curve that's really close to my point of tangency. I'm not going to go too far away, because if I'm using my line, I'm actually going to get points on my line, whereas like my curve would yield a different value. If I go too far away, if I try to use this tangent line to approximate a point on my curve, I'm going to get a point on the line when my curve is like way, way, way up there. So anytime we do this, we only want to do a tangent line approximation when we're really close to our point of tangency. So x equals 3.1, well, that's pretty close to x equals 3. All right, so when we do this, we want to show what we are approximating. F of 3.1 is approximately equal to, we could say y equals here, and then I have 57/4. I'm going to substitute 3.1 for x, and then I'm going to add 18 to all that. So 3.1 minus 3, well, I guess I should keep my 57/4. 3.1 minus 3 is just 0.1, which is the same as saying 1/10. Sometimes it's easier to go, we need to either go all fraction or all decimal there, in my opinion. All right, so 57/4 times 1/10 is just 57/40. I always think going all fraction is easier. Got to add 18 to that. And honestly, if this was a free response question, I could leave my answer like that. But if I get common denominators, 18 times 40 is 720. So this becomes 57/40 plus 720/40. And we would get 777/40. Oops. So our approximation for f at 3.1 using the tangent line is 777/40. But what we know is that our actual value for f is going to be something a little bit different. And later on in this semester, we'll start to talk about if we have an over or under approximation. But for now, let's just use our tangent line to approximate f. All right, in our second example, we are asked to just find the equation of the line tangent to g equals sine of pi x at x equals 1/2. So we don't have to do an approximation, we're just writing our equation. So again, to write our equation for a tangent line, we need our point of tangency. So we need a comma f of a. We're already told that a is 1/2. So I need to find, well, I said f, I'm going to say g, since our function is called g. I need to find g of 1/2. That will give me the rest of my point of tangency. And then I also need g prime of 1/2. So just kind of my little thinking bubble over here. All right, so g of 1/2 is just the sine of pi times 1/2, which is just pi over 2. And I know that my sine of pi over 2 is 1. In order to find g prime of 1/2, I need g prime of x first. So I need to find my derivative as a function of x before I can plug in my 1/2. So g prime of x. Well, I notice that I have a composition here. My outer function is a sine of x, but on the inside, I don't just have x, I have pi times x. So when I take my derivative of sine of some junk is cosine of the junk. So I'm going to keep my pi x times the derivative of the junk, so times pi. And we could just clean that up and think of that as pi times the cosine pi x. So now, if I wish to find g prime of 1/2, that's just pi times the cosine of pi times 1/2, which is just pi over 2. And the cosine of pi over 2 is 0. So pi times 0 is 0. So we find that we have a slope of 0, and we have a point of tangency. We said our point of tangency is at 1/2, 1. Okay, so when we go to write our equation of our tangent line here, I could think of that as like y minus 1 equals 0 times x minus 1/2. Now, on a free response question, you could totally leave your answer this way, but 0 times x minus 1/2, it doesn't matter what value I plug in for x, 0 times anything is 0. So I could think of this as y minus 1 equals 0, and I could write my equation as y equals 1. So that's going to kind of bring us into our next topic, that if I have a slope of 0, so when we plugged 1/2 into g prime, and we found out that g prime of 1/2 is 0, think about it. A line with a slope of 0 is a horizontal line. So I know that I have a horizontal tangent line if my slope is 0. So if my, in this case, derivative of 1/2 is 0, my line is horizontal. And I know that all horizontal lines could be written as y equals a constant. So in this case, y equals 1. All right, so as we dig in deeper to horizontal and vertical tangent lines, we just recalled that a horizontal line has a slope of 0. A vertical line, we might want to remember, has a slope that is undefined. So when something is vertical, I could almost think of its slope, of it having a slope of infinity, because it's infinitely rising and never running. So I'm just going to put a little note up here that if I have a horizontal tangent line, if I think about my derivative, I can think of my derivative as being 0. I could also think of it as being 0 over a number, where like b is not 0. So if I think of it as 0 over a number, I could think of this as almost being like no rise and all run. So a horizontal tangent line has 0 rise, so 0 on top, but it runs on bottom. Whereas conversely, a vertical tangent line, I could think of my dy dx as being a number over 0, where again, b is not 0. And I could think of that as where I have all rise, so I'm rising, but 0 run or no run. So that's how I could remember my 0 is on bottom because I have 0 run when I'm looking at a vertical line. All right, so as we're thinking about the equation of the line tangent to y equals x squared minus 4x plus 8 at x equals 2, and we have the graph of that quadratic function to our right, if I just look at my graph at x equals 2, well, I bet I could, we're going to do this without just looking at the graph, but I bet I could figure out right now what the equation of my tangent line is, because x equals 2 is the vertex of that parabola. But let's say we don't have that graph, and maybe we're not sure. I know that if I'm writing my equation of my tangent line, that I'm going to need to find y of 2. That's going to give me my point of tangency. I'm also going to need to find y prime of 2. That derivative is going to give me my slope of my tangent line when x equals 2. So to find y of 2, I just plug in a 2. So 2 squared minus 4 times 2 plus 8 is 4 minus 8 plus 8, which is just 4. So our point of tangency is at 2, 4. To find y prime of 2, I first need y prime as a function of x. So we get 2x minus 4 for y prime. So y prime evaluated when x is 2 is just 2 times 2 minus 4, which is 0. So again, I could go back to my point slope form of my equation of my line. I could think of this as y minus 4, and again that's 4 from our point of tangency, equals 0 times x minus 2. That 2 is the input of our point of tangency. But that's the same as just y minus 4 equals 0, which is the same as y equals 4. So anytime we have a horizontal line in general, we could again write our equation as y equals a constant, and we'll notice that at y equals 4, that horizontal line is going to just touch our parabola at the vertex, and that is our tangent line there. If we look at this next example, we are asked to find the equation of the line tangent to f at x equals 4. Well, if I look at at x equals negative 4. If I look at the graph to the right, I can tell something interesting is happening at x equals negative 4. In fact, it looks like if I think of my derivative being, if I think about how I can take the derivative where I'm locally linear, it looks like right here, even though this is a curve, if I were to draw a line through this spot where we are locally linear here, that is a vertical line. So I know something interesting is going to happen when I find my derivative. All right, so again, if I'm writing the equation to the line tangent to f at x equals negative 4, that means I need f of negative 4, and I need f prime of negative 4. All right, so as I find f of negative 4, that's just 2 plus the cube root of negative 4 plus 4. Well, negative 4 plus 4 is 0. The cube root of 0 is 0, so that's just equal to 2 plus 0, or 2. When I go to find f prime of x, so I guess let me back up. We said our point of tangency is at negative 4, 2. So now finding f prime of x, I might first rewrite f of x to have a power, x plus 4 to the 1/3 power, instead of the cube root there. Because again, I don't have a derivative rule for radicals, I have a derivative rule for powers. So when I go to find my derivative, f prime of x, well, the derivative of 2 is just a 0, that's a constant. When I get to the power piece, I've got 1/3 times x plus 4. I subtract 1 from my exponent, so the negative 2/3 power. The chain rule tells me to be cognizant here and to multiply by the derivative of x plus 4, but that is just 1. So I should do it, but it is just the number 1. So f prime of x is 1/3 times x plus 4 to the 2/3 power. And I might need to remember that that's the cube root of x plus 4 squared. So now, when I go to find f prime of negative 4, I have 1/3 times negative 4 plus 4 to the 2/3 power, which is 1/3 times 0. Because negative 4 plus 4 is 0, 0 to the 2/3 power is 0, so we end up getting 1/0. So we know that if I get a 0 in my denominator, that I'm working with something that is undefined. So my slope is undefined here. So I just really need to remember what that means when I'm working with tangent lines. So for my slope to be undefined, there's actually only 2 ways that that could happen. My slope could be undefined because I could have a vertical line. So for example, my derivative is undefined, or my slope of my tangent line is undefined when my line's vertical. Because technically, the slope is like infinity, and infinity is not a value. The other time that this could happen, that our slope is undefined or that our derivative is undefined, is going to be when our function is not locally linear, and we'll look at that in a few minutes. So if I look at what's going on at x equals -4, we said that we have a vertical line here. And anytime we discover our tangent line is vertical, and again, we said the way to know this is that when I find my dy dx or my f prime of x, when I plug in a value, I get a number over 0, kind of like when we have a vertical asymptote. So if my derivative is 1 over 0, my slope is essentially infinity. So if I have a vertical line, I just need to remember that the equation for a vertical line is always x equals a constant. So in this case, x equals -4. So our equation is always going to be x equals the x value that our vertical tangent line passes through. And if I look at my graph, again, x equals -4, this is a line where every single ordered pair on the line has an x value of -4, like -4, 0, or like right here would be -4, 2, or up here would be -4, 4. So if I control my x's to be -4 and y's can vary, I'll have a vertical line.